I have a great pleasure in introducing Professor Slobodan Simonovic. He's not an easy person to bring here because he's such a busy person, even though he's only an hour away. So I'm so happy because we haven't seen him for, I don't know, more than 2 decades probably in Waterloo. So he's a well-known civil and environmental engineering researcher and engineer, and of course is a professor at the University of Western Ontario. He's also director of engineering studies with the Institute for Catastrophic Loss Reduction. So, you will obviously see his expertise come through in these talks with the things on natural hazards. He has been working for more than 35 years in this field, and he originally, I think your PhD is from California Davis, UC California Davis. He's one of the leading water resources engineer in terms of applying systems analysis for many different kinds of water problems with multi-objective optimization and all kind of difficult problems to solve. So not only that, but when he was in his previous life, he was at the Winnipeg, University of Winnipeg?
No, Manitoba.
University of Manitoba, Winnipeg. So he had personally seen probably some floods there.
Oh, yeah.
So no wonder he is completely thrilled about working to help people get over some of these difficulties. Of course, it's not that easy. On the research side, he has more than 500 publications. He has one of the highest H index in water area, like 52. And also, he has been introduced into the Canadian Academy of Engineering some few years ago. So I don't want to delay further. I'll let Slobodan talk about it. Thank you.
Thank you very much. Thank you very much for the invitation. It's a great pleasure to be here. I have a lot of friends and colleagues at Waterloo, but unfortunately, physically, we are not communicating as often as we should. Talking to Professor Panu, I was thinking to share with you a little bit of the current research I'm involved with. And one of the products that recently made public. So the presentation will be more like introducing the idea of resilience and how the resilience can be used in dealing with the municipal infrastructure, and more general as a kind of decision-making criteria. I do deliver this type of presentation under different title too. Trying to actually bring the resilience to the level and place where each society that's now subject to changing conditions should be probably thinking about resilience, but not only in a qualitative form, but in a quantitative terms, so that can be then used as a support for decision making. For those of you who may be running for lunch, these are the conclusions of my presentation. I am trying to say here that there are some kind of practical links between the adaptation to changing conditions and sustainable development, and that these links, I think, are, in my view, reinforcing resilience as a new, really development concept. In thinking about resilience, or thinking about resilience in quantitative terms, is bringing again, I think, attention to systems analysis. And I'm definitely biased by my education and the work over the number of decades, where I see, tremendous value in utilizing the systems approach. In utilizing it in this concept to kind of capture the temporal and the spatial dynamics of the disaster management, to better understand the factors that are contributing to resilience, as well as using it as a kind of more systematic tool in making decisions. But we have to still remember that understanding the local context is really essential. Local context of vulnerability and exposure, because that affects and gets into this quantification of the concept, and very much affects the way how it can be used. So to mitigate damages, resilience to disaster, should be integrated in almost every step: planning, design, operational policies, and so on. So that's what I will be talking about. I organized the presentation in the form of walking you from risk management to resilience, a little bit on quantification of the concept, and then through the example of the tool, public tool that we have developed, I would kind of present how this quantitative concept can be used in decision making. I do have a lot to say about this particular tool and my multi-year attempt to involve the city of Toronto to work with us, and unfortunately, that's not an easy task. To give you the context, these are the type of projects that I was involved with, within which we worked and utilized this or developed this quantification scheme, introduced this idea of resilience to various areas of potential application, and also worked with decision makers in developing tools that can be used by them. So I'm leading the two projects, one for collaborative research project with the BC Hydro, where this concept of resilience is being used to assess the safety of the hydropower infrastructure, especially dams, and how this concept can be basically resolving the problem of having a $63 billion in assets and having approximately less than $10 billion over next 10 years to maintain the assets, and assets are about 50 to 60 years old. So you understand that the issues related to safety are very serious issues that they have to deal with. The second project I'm involved with is the project funded. It's also the kind of collaborative project, but it's funded with the reinsurance company, Chaucer, and they are very much interested in actually seeing how different type of natural disasters, with a focus on weather-caused disasters and earthquakes, how they can be incorporated into their business model, and the way how they offer products, how they structure the products, and how they determine, what products should be done. So these two projects are relatively close to the end. This one is ending in about a couple of months, and this one will take a little bit more time to kind of finish. We worked also on these two projects. I am the principal investigator, but I was also participating in the two other projects where this concept of resilience has been implemented. The Coastal Cities at Risk project was the project where the city of Vancouver, Manila in Philippines, Bangkok in Thailand, and Lagos in Nigeria were considered together in order to assess the impacts of climate change. They're all coastal cities with very large rivers flowing through, and therefore exposed to the impacts of the kind of sea level rise, flooding, riverine flooding, and all the kind of other issues. So for this particular project, I think for the first time, we developed this quantitative resilience measure and then applied in these different cities, in different setups, with a different type of data and information in order to assist the municipal decision makers to deal with this long-term potential impacts. And the final one is a collaboration led by the York University, where again, we utilize this resilience concept in basically response or to natural disasters, and try to illustrate what the example that I'm using at the end of this presentation is actually showing is something that can be used. It can be used in planning purposes, but it can be used also for response and recovery stage. So this is giving you the kind of, the illustration how different type of projects are being built around the same concept that I will be introducing and talking about. For the audience like this, I don't think I need to provide a very kind of detailed introduction. The changing conditions around us are calling, I think, for a different points of view. We have a tremendous increase in population, land use change, urbanization, climatic change, and all these kind of changing conditions I think are basically affecting two things. One is the complexity of the systems that we are dealing with, as well as the uncertainty that's involved in many aspects of these complex systems. And when I'm talking about these complex systems, I am talking about basically infrastructure systems, both hard and soft. Where under the hard, we consider the water infrastructure, energy, transportation, and so on. And under soft, institutional, organization, social, and other type of infrastructure that also needs adaptation and response to these changing conditions. And since Professor Ponu mentioned my involvement with the Red River flood, this is the picture from 1997 flood of the century in the Red River Basin. This is the time when I was professor at University of Manitoba. And this is the picture that basically changed my professional life. I was appointed by our Minister of Foreign Affairs to serve on the IJC committee for 5 years. After the flood, we worked to come up with the recommendations to both governments of the United States and Canada, and had the opportunity to kind of travel through the watershed, both parts, Canadian and US part, to talk to people who lost everything, to people who were responsible for something like this. This is downtown of Grand Forks. Grand Forks is the city that's still in the news nowadays because of the potential flooding and the issues they have in moving the people from the floodplains. And the downtown was lost to fire because the fire trucks were stuck in the floodwater. So this is the picture that was published on the first page of the Winnipeg Free Press, and picture that actually affected the whole population of Winnipeg and the rest of the population in the Canadian part of the basin. And for me, it was a kind of illustration, how easy it is to teach. This is what I do, to teach my students how to design a dike or how to operate some piece of, flood protection infrastructure. But how to explain to them, something like this, or how to explain how I felt when the people were talking about losing everything, lifetime possessions in a single event that basically erased, the generations of economic growth, family type of economic growth, and so on. So that probably affected the rest of my professional life. And I did a lot of work related to managing risk, dealing with the issues and events like this very large flood in 1997. And you are probably aware that risk management is already part of, kind of decision making, and especially in dealing with the complex water resources problems like, droughts or floods or, response to extremes and things like that. But in this type of context, we are relatively simplifying the whole problem by looking on one side hazard, the probability of hazard, coming up with the best way of estimating it, and then looking into consequences of various types and trying to combine them together in some measure of risk. At the end, still kind of producing the relatively simple static picture of the situation of that system. What you see here is the city of London, where I am now from, and the different shades of red are showing the risk to climate change caused flooding along the Thames River that goes through the city of London. And when we generated this type of product, you see that you have opportunity to identify the areas that are of higher risk by clicking on these areas, identifying what is contributing to this particular risk. And the city was very happy with maps like this. This map is showing the total risk for one particular scenario, hydrologic scenario and climate scenario. We were able to generate many maps, for example, focusing only on roads or water infrastructure or any other kind of issue that was of concern to the city. But at the end, these different shades of red are nothing else than a single number which is kind of including everything the type of hazard, the dynamics of the hazard, and a set of different impacts, interactions between impacts, and a way of kind of putting these hazards and impacts together. People liked it. We had a number of public presentations. We brought these maps, and people were very involved in identifying, oh my God, my house is somewhere here, and what is causing that risk. And they were able to see, for example, at this location, we have a railway going through downtown London. Under the railway, the culvert, and the culvert capacity insufficient to possibly carry the flood of that magnitude, therefore causing the potential flooding of these residential properties. And the reaction was very interesting. Oh, railway is a federal responsibility. Let's talk to feds about this and finding the solution and so on. People from Upper Thames Conservation Authority responsible for flooding liked it. They see here, my God, in the floodplain, London has 6 wastewater treatment plants, all of them in the floodplains. So with a potentially larger magnitude flooding, these very expensive facilities can generate considerable level of risk. And it was almost immediate reaction. We should try to do something. I mean, moving these facilities is not so easy, but we can do some kind of small adjustments, raising the electrical and mechanical equipment to higher level within the facility, within the building, can possibly reduce. And they attempted, and they did a lot of these small adjustments to respond. So I'm trying to illustrate that even in this kind of static form, in a single number, and in a map with different shades of red, the tool and this kind of level or assessment of risk was useful for decision makers. However, I feel there are still a lot of issues there. First, this kind of static nature and representation of the risk as a single number. Difficulties in coming up with the probabilities of extreme events when we are very much aware how many observations of extreme events we have. Difficulties in integrating kind of social, environmental, economic, ecological concerns together. So that led the whole kind of switch, at least in my thinking and the research, towards something, to a measure of a different nature. And that measure, at the beginning, needed to satisfy the needs to be dynamic so that we can capture the development and how the event goes from the kind of beginning to the end and full recovery, and also ability to deal with the direct and indirect losses, basically build the broader framework that can be of multiple value to decision makers. So what we have done, we basically replaced the one shade of red in that previous map with a graph. And this graph is now the representation over time. The horizontal axis shows the time, and the vertical axis showing the impact, and it's capturing actually the whole event. So the idea here, let's say, I'm sorry. Let's say that we are measuring the number of kilometers of roads that are being inundated due to the kind of flooding within the urban environment. And if this is the beginning of the flooding event, we will be losing, or obviously the roads will be inundated until we reach the maximum kind of flow that will be representing the maximum extent of damage. And after that, the slowly system will be recovering back. So instead of having a single value of risk, now we have a multiple, thank you very much. We have a multiple source of information. We are capturing the dynamics. We can see the slope of this curve, which is called the redundancy, that measures how fast you are losing the performance, how fast the roads are becoming, impassable or flooded. We have a measure of, what is the maximum extent of that particular impact. We have the measure how much time it will be recovered for the system to come back. We have also opportunity to see, will the system be able to come back? Or maybe simply end up with a level of performance below the initial performance. Or if we put some resources, financial, human, mechanization, whatever, into this particular part of the event, we can actually change the slope, and we can maybe build the capacity of the system to a higher level than before. So you see, we are replacing a single value, single kind of risk, with now full description of the system response to kind of change or changing condition. And that's exactly what was used in the kind of quantification. I'm not going to go through the definitions. The term, origins of the terms are relatively old. Mechanical engineers are fully aware of, and civil engineers, from mechanics, the work of Rankine. And then we had people in ecological domain, followed with the hazard domain, where the resilience started becoming more and more popular term. At the end, what I'm using in this definition, and I think you probably already sensing from the previous graph, I'm defining or expanding the definition of the United Nations disaster research of kind of seeing resilience as ability of the system to respond to change or changing condition in a way of mobilizing the resources within the particular time frame and trying to come or return the functioning of the system back to initial stage. That type of definition and the graph that I did show up can be developed for multiple impacts. I gave the example of roads being inundated. We may be showing the performance curve using as a measure number of beds in the hospitals for people who may be injured during the disaster. We may be using the number of or the time of this disturbance to information network or the communication network. So you can develop various impacts, link them to a particular hazard under consideration, all of them having different units and having a similar shape of kind of performance graph. So now the logical question is, how can we kind of convert that into a single measure? How can we put these different units together? And the idea is relatively simple. That's the idea we implemented in quantifying this. We consider this white area here as the loss of performance. And then the shaded area as a remaining system performance, and I named that resilience. So by simply integrating the area under the performance curve gave us some measure what is happening with the system over time. You can actually get this value for any time within this kind of time frame, and very easily now normalize that value and representing all impacts on the scale between 0 and 1, which gives us opportunity to now mix them or put them together or show them independently as you wish. So the quantification is based on this kind of system performance and adaptive capacity, which are determining the shape of that curve, and analytics are relatively straightforward. Integration of the area under together with the normalization. That's implemented in now systems simulation kind of context with 3 feedback relationships here linking impacts, resilience, and adaptive capacity, where 2 of them are destabilizing the system. These are the blue feedbacks, and the big red one that's actually trying to push the system to some more stable state. In analytical form, adaptive capacity and the impacts are kind of together, giving us that measure of resilience. So that's a short walk through the quantification process that now allowed us to think about how to use this concept. We started very early with this project on the coastal megacities, where each city was considered to be the kind of system under consideration. 4 impacts were put together, the physical, social, health, health and environmental. We had a very interdisciplinary team. We worked with 2 doctors who were looking into health impact, 4 social scientists, 2 political scientists. I was even co-advising the thesis in political science, being an engineer. That was really a challenge. But the point was that this kind of concept did help us to put these different perspectives together. It took us about a year to develop the understanding and vocabulary and agree on, because economists were talking about same things as we engineers, but using completely different language. Our colleagues in social science were also talking about similar things, but using another way of expressing their kind of concerns. So that kind of prompted further motivation to try and build something that will help those who may want to implement this. So the implementation that I am kind of covering in this presentation is available in the public domain in the 2 forms. You have here the websites you can access very easily and see what we have developed. The first one is a prototype system that only deals with kind of flood disasters, with 2 options, looking Toronto and London, Ontario, and also seeing how, for example, different adaptation options can be investigated in order to respond to flooding in these 2 cities, utilizing this measure of resilience. The second one I'm going to walk you through, it's much more detailed, and it's much more general. What we have done, we kind of accepted the same idea of resilience, or implemented the same idea of resilience, but implemented in such a form that the user can identify the hazard. So the hazard can go outside of the domain of weather-caused hazards. You can consider terrorist attack. You can consider some chemical spills. You can consider any possible hazard that may occur, and the kind of same idea in the same context and the same concept of resilience can be used in investigating various response actions and adaptation measures. The systems are, both of them are developed in the form of this decision support, where you are combining 3 kind of key groups of tools, the graphical user interface to assist those who are using the system in preparing the information, processing the information, generating outputs, extracting the outputs in the form that is of use for them. Database, which is kind of permanently being updated with the information that's available, and so-called the model base, where all the kind of necessary calculations are stored, like calculation of resilience as I presented it, as well as various impacts that are being considered. This is the view of I'm just going to walk you through a few of the screens. Presentation of this nature does not allow me to go into the demonstration, but I would strongly encourage you, if you have interest, to actually access the tool, this particular more detailed tool. Both actually have the user manuals, also downloadable. And in this particular case, there are 5 examples which are already provided on the web, so that they are nicely kind of illustrated various ways of using this, this particular tool. And the user manual is describing all these 5 examples, so you can kind of nicely go through if you're interested. So the key starting point through the graphical user interface is to build your system. And building the structure of the system is, in our case, restricted to 2 different formats. One is networks. That applies to kind of roads, electrical supply, water supply, information, and so on. And another, we call them kind of layers, basically spatial representation of the information. And I thought these two formats are sufficient basically to cover everything that may be of interest. And relatively recently had a presentation where the colleagues from the wind engineering were sitting in the room, and they asked me, is this network and spatial, is this kind of sufficient to represent all the details of the system? They were looking for a third dimension. They were actually looking for the height of the building because that generates the exposure to wind and basically is the main source of. So obviously there is space for improvement and expansion. We do not have that right now in the system. So the spatial data includes like buildings, critical facilities, schools, digital elevation model, and all the information that's available in the graphical, or sorry, in the spatial form. I should probably tell you a little bit about. I made the presentation of the idea to the city of Toronto 7 times. I was talking to first different groups. I know that the city of Toronto is one of the 100 resilient cities according to Rockefeller Foundation. They appointed a resilience officer. I was hoping I will have a chance to talk to the resilience officer, but that was not possible. So after about all these 7 presentations and year and so, we were not even able to get the digital elevation model from the city because it required 5 levels of approval in order to be shared with someone outside of the city. Very, very strange, at least for my understanding of the functioning of the municipal government. But anyhow, we decided to forget that in the project and to go on. And what we have done, actually, we now entered into something that's known as a kind of public information of this nature. This kind of information is widely available, and that is being used to populate our database, and everything is based on this kind of public information. That allowed us to complete the project and have the functioning system that can be obviously, if one day city decides to go that direction, that can be modified or improved with populating it with their own data. So the first step in the process is definition of the system. So through the set of screens of this kind of nature, you are now entering the information about your system. As you can see, on the left-hand side are networks, and you can edit, remove, add all the kind of networks that are part of your system or concern. And the second type of input is related to the spatial information that we call layers. Again, with a very flexible format that can take any type of information that is of importance. Vulnerable buildings, fire stations, schools. Over there you have information networks, high voltage transmission lines, oil supply lines, and so on. So basically, we prepare the ways that information can be imported in a particular format that's kind of explained from other sources, or directly basically entered into the system by, if when you click on the edit button, the additional screens are coming up that allow you to enter the information in a very detailed form. When you have the system set up, when this information is in the database, then we proceed with basically identification of the hazard. That's a new part in this particular version of the tool, and the reason we kind of build this as a user-provided input is to allow system to really consider various hazards. So there is no any particular limitation what type of hazard you may be using the system for. There are a couple of very interesting options. One is to identify by simply plotting on the map the affected area. So if you have someone dropping the bomb somewhere down there, the area affected can be immediately mapped. and identify it. If you have a rainfall event hitting, the southern part of the city, you can kind of very easily enter this particular information. So one form is in this kind of graphical form. Another one is if this is used for, let's say, planning purposes or something like that, you may have the historical kind of data or historical events that you can kind of import as the hazardous events into the tool to do the analysis. So for each of these kind of events, we have now the number of additional pieces of information that's required, and they are basically ways of characterizing, or the ways of describing the hazard. In this particular case, you have basically I think this was a small, precipitation event that happened in August when we were finishing the system, and we kind of captured what is the water depth that was occurring over the duration of the event. On the other side, you had a number of different ways to enter the potential impacts of the hazard. If the hazard generates the physical damage, you describe what type of physical damage, you describe and you provide the information for assessing the damage. The information can be provided in a purely economic form, like depth-damage relationships in the case of flooding, or fragility curves in the case of, kind of wind disasters, which are more or less probabilistic type of expressions. You can provide, as you can see, physical as well as the functional impact. So anything that particular hazard may kind of generate on the system that you already kind of provided to the tool needs and goes into the system through the communication with this particular interface. Now, we have a system defined, we have a hazard defined, and we are coming now to the most interesting part, where, again, portion of it can be designed by the user. And that's the part where we are utilizing this resilience concept by simply creating the set of measures to respond to the hazard under consideration. So the right-hand side part of this screen is basically user's choice of various measures, how you are responding or how you want to respond to different hazards. We were talking about, let's say, investment in the maintenance of the drainage network, or you can talk about number of transformers being protected by, the kind of higher elevation. When we were working with the insurance guys, they wanted us to put, for example, the time required to process the claims. So, various ways how you respond can be directly put as different types of adaptation options, and that immediately gives you opportunity to do the calculation of resilience and see how these different options compare according to resilience as introduced. So what you see on the left-hand side are the now outputs of the analysis. Yellow line represents the resilience of the system without any kind of adaptation options or subject to the particular hazard, which is the kind of current state of the system without any in addition. And the blue lines are representing now the outcomes with the selected choices of potential adaptation options. So you can see now, you can very easily, this is all happening in real time. If you go into the system that you just click and you get the lines being plotted. The information on the slope, on the redundancy and the timing and so everything else is also provided. The resilience of particular elements of interest or particular impacts are provided, as well as the total resilience. So you have various options of creating the outputs that can help decision makers. So my view of this for the city of Toronto would be that you have the system implemented, and then on your tablet and phone, those who are responsible can immediately respond to event, go out, capture the extent of the impact, enter this information, and almost in real time make decisions. Should we bring more pumps, or should we mobilize more people, or should we do something else to respond to the situation? Or in the case of planning and sitting in the office, you decide, for example, you have this budget for dealing with the hazards. How should we invest? Should we put that into the early stages of reducing the slope of the loss, or should we put all the money in the response and trying to bring the system back, as fast as possible? So very easily you can experiment with these various options. First, you can choose various options. You can bring different perspectives into that kind of response, and then you can kind of integrate them together and basically use the resilience as the measure that can help final decision. I'm not saying that this should be the kind of single, criteria for the decision makers, but this can be very nicely integrated with other points of view. You can easily, bring the economics, costs, and potential limitations of the budgets into this type of analysis, and then see how that may be interacting and affecting the resilience. You can deal with the kind of various options, like deciding if you have a multiple impact, health impacts, social impacts, some environmental impacts. What are the trade-offs? If we respond in this way, how resilience will be what part of the system. So you can do multiple kind of analysis with the kind of same framework as it is built, if you accept that kind of quantification and the definition of resilience as I presented earlier. So this brings me to the end of the presentation. I was trying here to illustrate that there are some kind of links between the adaptation to globally changing conditions and sustainable development, that in my opinion, this is a very good or very serious call for looking into resilience as a development paradigm. I have a very strong bias that systems analysis, assessing all these impacts that I'm talking about in the previous kind of illustration, requires models. These models can be simulation type of models, which are basically helping you to calculate the impacts. So the kind of systems approach, systems thinking is definitely present from the beginning, from the point of view of designing your system, identifying how far are you going to go with the network, how many different network and are you going to consider, and so on. That helps us in understanding the kind of temporal and spatial dynamics of resilience, contributions to the resilience, or what are the important factors contributing, and I think at the end offers opportunity to serve as a tool for decision making. In order to do that, you have to take care of the local context, and I think that example that I presented is nicely illustrating the importance of the local context. You see that you have to have, I use the city of Toronto, then we build the networks and utilize the information for the city, and that allows you to kind of go with hazards and so on. I feel also very strongly that the tool and the approach can serve a variety of decision-making questions, from planning, designing, operating complex infrastructure systems, and also ability to integrate together various aspects. These are some of the publications that are talking about the quantification that are already available. In yellow is what my lab is publishing as a blue books. They're called Water Resources Research Reports. They're available through our library or through the website, my personal website, or the website of the laboratory. And these blue books are very detailed. So the yellow one is, for example, the basically manual for the system that I kind of walked you through. In the case you have interest for more details, I'm very much open and I can respond to emails, simonovic@uwo.ca. And also a lot of information is available on my website as well as the website of my laboratory. FIDS is the Facility for Intelligent Decision Support. That's actually the computer lab where my graduate students are working. With this, thank you very much for the attention. I'll be happy if we have time to answer some questions.
Thanks, Slobodan. Okay, I'm supposed to give you this for making sure your questions are loud. So please.
Okay, thank you very much, Professor Simonovic. Actually, as you know, traditionally, at least in the water reservoir systems management, we have three traditional performance criteria calling vulnerability, reliability, and resilience. And that can be generalized to any other infrastructure system considering severity, frequency, and how fast a system can recover after a failure. That's how traditionally we define, for example, resilience. Of course, yes, one problem was that these traditional criteria our point was average in time and also for lamped system versus distributed. Now you recommend resilience and changed it from 1.2 to a matrix having both temporal and spatial dimensions that can be done perhaps even for reliability, this to generalize. But my understanding is that, okay, all these criteria, and even there are some works trying to extend these three and put them in one index called sustainability index. And there are some works doing for example, objective optimization to account for all of them and combination. One aspect is that how to combine these criteria, each one accounting for one consequence of failures. That my understanding is that, okay, the resilience, the way that you define resilience as the system capability to absorb the disturbance somehow is to combine all these three criteria in one criteria and then extend it to having both temporal and spatial distribution. Am I right, or this is something else?
You're right. The only difference, I'm sorry I realized I didn't put, we published a paper in Water Resources Research on using actually the reservoir example, and we were pushed to compare the traditional resilience measures that exist from 70s with what we are offering. The key difference is capturing this dynamic character by considering, this measure as a dynamic measure over the period of time, whereas the traditional resilience measure is a kind of single number, very similar to risk, but measuring different aspects of it. So that's the kind of key difference. Now, that kind of spatial as well as the kind of temporal dynamics, I think, are essential when we are dealing with natural hazards and hazards of non-natural nature. That's, I think, the reason, and that's what I am trying here to say. That pushes us towards the simulation, very strong support, by simulation and simulation modeling that will assess different impact, that will produce this, response curves and performance curves and so on. But the key difference is now this dynamic character, the whole kind of representation over time versus the single value. If you look at our traditional measures, they will be like on my graph, if you remember the graph, there will be a single value corresponding to one moment in time.
Thank you. Well, one good news is I actually logged in now to your system, except that I don't think it's meant for a small iPhone, so you can. I mean, it's just like, it's a bit hard to do. So I will wait for a bigger computer because it looks like really nice system that you've developed, and it's really amazing. And also taking all the theory and papers. We write lots of papers, but hardly anyone reads them. So this kind of way is a good way to transfer research to people who can immediately apply in some way. And then, of course, also to, to make it as an educational tool. Yeah, thank you very much. Any more questions?
Yeah, I still need the microphone.
Okay.
I think I can talk loud enough.
But they would like to tape.
Yeah.
Oh, the tape they needed, I think, for them. Sorry.
Does your model ever show a case where you, show a case where you have to abandon the city?
Well, there is a possibility. depends on the type of the disaster. Like I did show the different projects I'm currently involved with, and one is with the BC Hydro, and they like the idea, but they said we are really not interested in anything after that loss of performance. We want to see they worry about dams and what may happen, with the dam. So they said, if the dam is lost, how is this going to be recovered, rebuilt, or decommissioned, or something? This is a purely political, long-term process. We don't care about that. They are very much interested, is the system failing immediately? What can we do to kind of change the slope so that you can actually protect either people downstream or deal with the infrastructure and save some of the infrastructure and so on. So yes, the answer is yes, that curve may have a single drop to zero. You lose the performance, completely. And that's basically what is happening with, the disaster that completely destroys the system. City is a little bit more complex system of multiple subsystems that are kind of working together. In our simulations, we were only focusing on, different type of hazards that maybe we simulated wind. We simulated basically Hurricane Hazel from 1954, wind and water, and we simulated earthquakes and water. But they were only kind of focusing on the particular parts of the city, nothing that would completely wipe out Toronto. But there is theoretically, there is no limitation.
Yes, thank you very much. It was a very great talk.
Thank
you. I actually had a question about the economics behind this, because you pointed out that it is possible to add dollar value to the effect of one particular option to just increase the resilience, right? Is there the possibility of putting a dollar value to the loss of the performance too?
Of course.
Yeah, because my understanding is that if resilience has to happen, but at what cost, right? If you have a nuclear plant or wastewater treatment plant, we have to just save it from inundation at any cost. But if there is some recreational activities within riverbanks, then we can just.
Yeah.
So where and when do the policymakers incorporate the dollar value?
At two places. First in definition of the hazard, where you can actually show and represent the impact of hazard in economic terms. So this is, for example, in flooding, that's relatively common through the stage damage, the water depth damage curve. So with the water of this depth, you lose so much of the property value and so on. So in defining that hazard, you remember I did show some screens, and this is where you can actually put the dollar value versus the impact of hazard. And the cost and the response comes in the last or the ending part, where the adaptation options are kind of being defined. So one adaptation option could be the investment into pre-disaster activities, or in response, or planning increase in budget or decrease in budget. So you have ability through this kind of resilience to balance now the kind of economic losses versus the costs that the system. I think this is also very useful because, and we can show the resilience, for example, only corresponding to one of these adaptation measures. So then you can compare to others. Like if you are considering the social and health impact and so on, and you can see the kind of material or economic damage. So then you can actually do some balancing, or you can integrate everything together into a single measure. But very easily, that's part of the system already.
Any other questions?
I think that's
Sorry, I was just curious. So with like the flooding that did happen in Toronto last summer or the year before, did you get any leeway with the City of Toronto by showing them how your model matched what actually happened on the ground?
We can very easily compare the kind of description of the hazard and the extent of the impact, but there is no any information on the response and how is the response organized, who is making decisions, like what we have on the right-hand side, the kind of options. No one is able to actually give you that. In our case, especially in the case of flooding, I can talk about that forever. We have a very responsive type of approach. You actually experience the damage in Toronto, basement flooding and so on. Then you submit the claims, the insurance, and the insurance that kind of covers part of it, responds to claims, and the rest possibly with input from the provincial or federal government, depending on the extent of it. So this information, the insurance information, we worked very closely because I am associated with the institute that's supported by the insurance. We do have some kind of data from them, but this is very highly protected type of information. And city, as I told you, was not even ready to share the elevation of the, of the ground in the city. They were. We actually have some real TRCA data, especially on the inundation maps. They provided for all 7 watersheds in Toronto the 100-year return period inundation maps. The most cooperative group on that particular project was the how are they called? The Toronto. I'm sorry, lost it. The electricity supply, but not Ontario Power Gen, not OPG, but yeah, Toronto Hydro. So they provided us with the detailed maps of all the transformers, all the transmission lines connecting them, all the physical and technical information. So you see, we have this open street maps. That's the public type of information that we did input. But we did combine with the information that was provided. Toronto Hydro and UTRC data is integrated in the database.
For lack of time, this will be the last question. Sorry.
Thanks. I'm not sure if I read it right, but earlier in your presentation, when you first presented the performance response curves, and just generally talking about kind of a best case and worst case response back to normal, it looked like you were showing that it was possible to come back better than before. Is there an example of what that would be?
Yeah, there are different ways. Like the example could be type of infrastructure being used for drainage, or let's say dikes being used. In London, we are using dikes throughout the city. And in the case of flood event that happened, portion of the dikes are either destroyed or affected by it. So now they are making a decision to rebuild that. So you can rebuild to the previous level or previous standard of protection, or you can go for a higher standard of protection. So that will, on our curve, that will show actually immediately as the basically systems performance, which is higher at the higher level than the initial performance. That's a very simple example.